Our goal today is to convey three key messages. Number one, why we believe our compute solution is unique and offers differentiation at the edge for executing machine learning applications. Number two, how we leverage that differentiation to offer a compelling solution for our customers. And finally, a peek at the capability of our proof of concept solution, GrAI One, with two demonstrations. One for an autonomous navigation scenario, and number two for recognizing gestures. So let's get started. The edge, as everybody is aware, is a constrained environment. When it comes to AI computing at the edge, the three key aspects that we care about are power, because we are constrained in terms of the power we have available, the size, as in size of the end devices, and of course, performance. And we want to maximize the performance given the size and power constraints. Of course, the KPIs that are associated with these aspects are watts for power, or in some sense, milliwatts. The millimeter square, as in the size of the silicon chip. And the idea is to maximize this performance, which we typically prefer to use inferences per second rather than TOPS, which is used by a number of the industry players, because at the end of the day, what matters most are the inferences that you're able to deliver per second and or the latency of the system. So to summarize, the goal really of an AI edge computing solution is to maximize the inferences per second, per watt, per millimeter square. So let's look at some of the traditional approaches that have been taken to date. As people are aware, we have been using CPUs, GPUs, and DSP for different kinds of machine learning tasks, both in the cloud and at the edge. And what has happened recently is a multi-core approach to adding more CPUs, GPUs, and DSPs to improve the performance and simultaneously shrink the size using process node improvements. As you can imagine, they are fairly inefficient ways of going about tackling the edge workloads. The other approach has been to optimize excessively the AI math operations, typically referred to as MACC, which help in the matrix multiplications that are quite dominant in most machine learning applications. These tend to be geared towards specific models, example CNNs, and so you may end up with solutions that are really, really good at performing a particular task. The approach, another approach that has been taken is to combine storage and operations. And here it's an interesting approach because machine learning applications tend to use a number of weights and parameters that take up storage. And if you can combine the storage and operations, you can have an efficient architecture. This, however, is at the cost of using some exotic process nodes, especially in the analog domain. So what you end up with is what's shown on the curve demonstrated here. On the x-axis is the typical performance metric, which is TOPS, and on the y-axis is the efficiency metric, which is TOPS per watt. Typically, with the math optimizations and the process node improvements, you can push the envelope on the TOPS, as in the overall compute performance. In general, because of a number of different limitations, the ability to increase the efficiency of the TOPS per watt is quite limited in this approach. On the other hand, you can design an architecture with the math operations and some analog scaling approaches to basically leverage the efficiency curve and design solutions that are very, very good at a specific task. But what you really want at the edge is a lot more scalable platform, something that offers you, effectively a higher TOPS, but at a very high efficiency, which is the TOPS per watt. So how do you do that? What is interesting about edge data streams, unlike the cloud, is that most inputs have very high levels of redundancy. This is shown through the picture that's depicted here. Let us imagine you have a security camera monitoring the scene as shown there. Between frame to frame, what you will notice is there's very little change in the pixels that depict what is important in that frame. These changes in the frame are sparse, as you can see, less than 10% in this image. They're localized and they're highly correlated in space and time. We call this sparsity. Now, traditional architectures, however efficient they may be, actually process every pixel that comes in. This also means that the neural network is exercised across every pixel or groups of pixels that are being fed in. A great analogy for this is your email system, which is bombarded by spam. All you really care about are the emails that are specific to you and not all the spam emails. So in a sense, most of the architectures that are available today, you can think of as processing all this spam needlessly. And hence, a lot of the power is wasted or the latencies are very high. Well, how about an architecture that could process only the changes in the data that's coming in? We call this an event-based computation of networks and or sparse compute. And this is something that will be demonstrated today with GrAI One, our first POC silicon. So in a sense, extending the concept from before, what you see here is that the Gray Matter Lab solution, GrAI One, for example, has to process only the changes in the input, but also the overall neural network operations are minimized because only the changes that are necessary or the events that are coming in are processed. This takes advantage of sparsity in space, in time, in connections, and in activation. And we call this sparsity compute. So this indeed achieves the goal that we set out for, which is to maximize the inferences per second per watt per millimeter square. How do we achieve this? So our three architectural pillars to enable this is one, dynamic data flow, which exploits the data dependent sparsity at the edge, digital neuromorphics, which enables a scalable and cost-efficient silicon design, and an in-memory compute, which reduces power consumption and latency. So we are bringing indeed all the different aspects that we talked about earlier, but in a package that also leverages the time sparsity. So our heritage, of course, comes from neuromorphics, and we, of course, implement this in a digital form, which means that we do not rely on spikes, which has been the traditional approach of neuromorphic architectures, rather valued events, which results in a simpler programming model. In addition, of course, we leverage the in-memory compute, which is to make sure that the data that's being processed is right next to the compute units. And we have a massively parallel architecture to enable this through a network on chip that connects all these different nodes together. My colleague Saber Moradi will be presenting a lot more details on our architecture and how we leverage sparsity in here. Third, but not least, is the question of programmability. So does a user now have to think about programming this architecture in a different way? Does the user need special retraining for the models that are being used? And the answer is no. You can actually use your familiar and easy deployment model, which is to train your models using the GPU and CPU based systems that you have available today. Use Keras and TensorFlow, which are the frameworks that you're comfortable with, develop the model and the application code, and use the GrAI Flow SDK for edge deployments and production. So again, you do not have to retrain your networks in any exotic ways, except for what you would normally do for edge deployments. So in summary, GrAI Matter Labs transforms edge computing. And the three key aspects of those transformation are NeuronFlow, which is leadership in edge computing, as in the efficiency and the compute envelope by leveraging sparsity. A scalable compute architecture that's fully digital and does not rely on any exotic analog techniques. And last but not least, a GrAI SDK, which allows you to use an efficient and familiar SDK to enable many use cases. The GrAI One accelerator that's available today is a proof of concept that demonstrates the efficacy of sparsity in various environments. This system has about 200,000 neurons. It's developed using a 28 nanometer TSMC process and is about 20 millimeters square. The SDK, as described earlier, leverages TensorFlow as our input and allows you to map existing networks onto our chip. We offer a conventional programming and machine learning model, which allows you to directly import networks, an integrated simulator, and a debugger, including a graphical editor to make it easy to production. We do have a hardware development kit available today. A lot of this will be demonstrated through our demos. What's seen on the right is, of course, the GrAI One POC silicon, which is residing on a daughter card that is connected to a standard off-the-shelf Xilinx board, which is acting as a host platform for us and allows us to basically communicate with the external environment, as in cameras or audio inputs or LiDAR inputs or radar inputs. And one example of such is shown on the left, which is a regular camera that's been connected via USB to the GrAI platform. So of course, you'll be curious to see how this performs in reality. And for that, my colleague Christian Graeber will walk you through 2 different demonstrations. I hope you enjoyed them, and thank you again very much for watching us.